All right, so now we're going to talk about sound, which is a specific type of wave. So if you recall, we have already discussed that there are two types of waves. There are mechanical waves, which are waves that require a medium, which is just another word for atoms, particles, material, matter. So we need some sort of substance that we are going to force into oscillation, right? We're going to have something that's going to cause these molecules to begin oscillating or moving, or sometimes we just say vibrating. So, when we talk about sound, first off, I need you to understand that sound is a mechanical wave. So, it requires matter, okay? Now, within our mechanical wave topic, we had two specific shapes. We were looking at transverse waves and then longitudinal waves. Sound is a longitudinal wave. So that means that the oscillations are going to occur parallel to the direction of the energy that is being transferred. So when we look at our picture down here at the bottom, we have an image of a slinky where the slinky is attached on the right side and the person is holding it on the left. So the way that this particular wave was created was by the person pushing on the slinky so that it ends up moving forward, and it caused a group of our slinky coils to become compressed or squished. And so that is the beginning of our wave, and then from there the energy is going to cause that compression section to then be passed along the slinky. The coils themselves do not relocate to different places throughout the slinky. So when we say that the matter oscillates, that's what we mean. Remember, we clarified this in a previous lesson. Oscillating means that it is simply vibrating or bouncing back and forth, but staying within the same general area. The molecules themselves are not traveling across the room. The coils are not traveling across the slinky. They are staying in the same general location, but the energy is being passed along the way. Okay, so just a quick review of what a longitudinal wave is. So when we look at this picture over here on the left, we have a speaker that is going to create sound by causing these alternating areas of compression and rarefaction within the air molecules that are in the air around the speaker. So similar to the animation that we looked at on the lesson where I introduced longitudinal waves, we have a force that is applied that squishes or compresses our air molecules. And so what we see on the image here is that we have these sections where those molecules are really tightly packed in together. And so this would be our compression phase of the longitudinal wave. And then as a result of having those compressions, we are left with a space where the molecules are very spread out, where there's lots of space between them, and so this is our rarefaction. So we are seeing that we have alternating compression and rarefaction. Now I want to clarify, I did comment on this the other day, but just to be clear, this graph right here is not showing me a transverse wave. Sound is longitudinal. What this is showing is that we can graph the amount of pressure, where the compression phase is going to be high amounts of pressure. So these are the moments where we have the compression of the air molecules. And then the rarefaction phase is going to have less pressure. So these are the moments where we are in the rarefaction phase. But sound is a longitudinal wave. This is just a graph showing that we have alternating phases of air pressure. Okay. Anything that vibrates creates a sound. So this is why when I ask you guys to turn off your phones, I want them to be turned off during a quiz or a test. When you take the SAT test, ACT test, or STAR test, we tell you to shut them down, because for those of you who choose to just put it on vibrate, when your phone vibrates, it still makes a noise. That is because any type of vibration of the molecules creates a sound wave, okay? So one of the important parts of our wave that we discussed with our wave basics information is amplitude. So for sound specifically, amplitude is going to determine the volume. Now, what we can say as a general description of amplitude is that amplitude gives us the intensity of our wave. So if we are talking about a sound wave, the volume, how loud or quiet our sound is going to be determined by the amplitude. And that is just how much displacement. So basically how much motion those molecules are going through when they oscillate. The frequency of a wave will also determine something about our sound. So when we talk about things that are high pitched and things that are low pitched, so high pitched sounds are going to be like scratching your nails on a chalkboard, right? Maybe a really high pitched whistle, like a dog whistle. Those are going to be high pitched sounds, and so they are going to have waves that have high frequencies. And so if you recall, the frequency is how often the wave occurs within 1 second. So this means that our waves are going to be very close together. Very close together, because that is going to allow us to get lots of waves in a short amount of time. If we hear something that is a low pitch, so a deeper noise, so think like a deep, big dog bark, not one of those yippy dogs, but a deep bark from a dog, or James Earl Jones, right? Whenever we talk about voices for men versus women, typically women's voices are more high pitched, men's voices are more low pitched. So we're going to have more space in between these waves so that they occur less frequently. There are fewer waves within 1 second of time whenever we have a low frequency. Okay, so low frequency, low pitch. The way that we hear sound is because these vibrations travel through the air and then they hit something inside of your ear called the eardrum. That eardrum is then going to receive the sound, and within your ear you have these tiny little hairs which are then pushed by the air pressure, and that stimulates a nerve that is then interpreted by the brain as the sound. So sometimes people don't hear things the same as maybe the person standing next to them, and that's just because our brains make that interpretation for us. So whenever we say how something looks or how something sounds, that is up to interpretation of the individual's brain. But the signal itself is going to be determined by the air pressure that reaches the eardrum. Okay, so that's how we hear sound. You do need to know this fun fact here that humans hear, the average hearing range for human is 20 hertz to 20,000 hertz. And we'll be listening to some sounds in class as well. I also have some videos on the Canvas page that have links to some YouTube videos where you get some more information and get to do some fun hearing tests. Wavelength and frequency are inversely related. We said this in our notes for our wave basics. The fact that we're talking about sound does not change that, so we are still inversely related. The speed that sound travels is going to depend upon the material. So this is an important fact for you to know. So when we talk about how fast sound is moving, it just depends on what is it passing through. Is the sound passing through air? Is the sound passing through metal? Is the sound passing through water? All of those different materials are going to affect the speed differently. If we understand that this is a mechanical wave where the energy is being passed through the molecules, then we just take it back to our basics of the different states of matter. In general, if we have a gas, those molecules are very far spread out. If we have a liquid, those molecules are now going to be closer together. If we have a solid, those molecules are going to be very tightly packed in, so that when we talk about how fast an object transfers sound, we're really just analyzing what is the spacing of those molecules. The more dense the material, the closer the molecules are, the faster that energy is going to be transferred to the next molecule. Okay, so when we look at the data table over here, we can just kind of eyeball the different types of materials, and we can see that the more dense materials have faster speed for the sound to travel through it. So read carefully. If you have a question and it's comparing two different waves, but they're both within the same medium, then they're both going to have the same speed. Okay, what would account for them having different speeds is just the material that they're passing through, or it could also be the temperature of that material. So we are going to be doing a lab in class where we're going to do some calculations, or we're going to take some measurements, do a calculation to determine the speed of the sound, and then we're going to look at the thermostat in the room and figure out how fast the molecules should be moving based off of what we know to be the effects of the temperature. So similar to our different states of matter, we should understand that higher temperatures are going to cause our molecules to be less dense. So higher temperatures, our materials are going to travel slower because the molecules are farther apart. Colder temperatures, our materials are going to pass the sound more quickly because the molecules are closer together. You also need to know this fact right here. Sound has an average speed of 340 meters per second. So depending on what resource you use to get the speed of sound, you might get different values. Like I said, there's several different things that can affect the speed. So we in this class are going to be using an average value of 340 meters per second, unless the problem tells you differently. So if the question says that sound travels through the air at 336 meters per second, that's the value that you will use for your velocity. But if the question doesn't say, and it's just like, hey, I'm sitting in the classroom and a kid is talking to me from across the hall, and I need to know the speed that the sound is going to travel from that student to me in order to be able to perform the calculation. Well, they didn't tell me specifically how fast the sound is moving, so in that case, I'll just use the 340 meters per second. All right, so now it is your time to do the sound waves worksheet.